Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. And the Dream Police, they live inside of my head because I am dreaming about the calculus. Optimization part 3, the third example. Very important strategy here. Sometimes the variable to be optimized is in the form of a single square root function. In these situations, it is convenient to square the function and use the fact that if the function is greater than 0 for all x in the interval under consideration, then the optimum value of a of x occurs at the same value of x as the optimum value of a of x squared. What does that mean? Well, sometimes it might not be convenient to take the derivative of something in a particular form. But if we square it, it'll make it a lot easier. And what this is saying is if we square a function, the optimum value will still occur at the same x value. Okay, let me show you an example of that. Here I've graphed, just to make it easier, I did a parabola where we know the maximum is at the vertex, right? I graphed the parabola negative x minus 2, the quantity squared, plus 2. And I did the plus 2 to move it off of the x-axis. So if I go here to analyze the graph, oops, I got to go to tools here, analyze graph, maximum, it's asking which function, there and there. And the function occurs when x equals 2. I'm sorry, the maximum occurs when x is equal to 2. Now I've taken this same function and squared it, okay? And if we analyze the graph and find the maximum, this function, left bound, it still occurs at 2. The value is different, but we're not interested in the value. We're interested in where the maximum occurs, okay? And if you're still not convinced, I'm going to take and copy this function, okay? And then I am going to square it. How about that? I'm going to square it. See how I did it? It's squared. I'm going to graph it. And looky there. It's this brown function. Let me get out of the way. It's the whole thing squared. And I think you can see that the max is still going to occur when x equals 2. Let's go back and analyze the graph just to convince you. Maximum. This function, left of it, right of it, it still occurs at x equals 2. So that is a nice strategy we can use if need be, and I wouldn't be talking about it if we're not going to use it in this example. So here we go. An animal enclosure is a right-angled triangle with one side being a drain. So this is the drain here, so that is a border for the shelter. The farmer has 300 meters of fencing available for the other two sides. So make sure we understand AB is a side of the fence, BC is another side of the fence. The drain acts as its own border, so there's no fence there. If AB equals x meters, okay, show that AC equals the square root of 90,000 minus 600x. Okay, this is not that bad because if AB is x, and if from A to B to C is 300 from the 300 meters of fencing available, then the total length of the fence is going to be 300. Then BC is 300 minus x. Yes? So we know that x squared plus AC squared has to equal 300 minus x squared by the Pythagorean theorem. And so then AC squared equals 300 minus x squared, so that's going to be 90,000 minus 600x plus x squared. Okay, and then that's all I did is I expanded this, and if I subtract x squared from both sides, it looks like that. So these guys go away. I take the square root, and AC is equal to the square root of 90,000 minus 600x. And I didn't have to put plus or minus because it's only positive, because this is a positive, it's a length, which is a positive. And we also, length is always positive, I'm sorry. And we also know that 0 must be less than equal to x, must be less than, or not equal to, but 0 is less than x, which must be less than 300, since there is only 300 feet of fence. Find the maximal possible area of the triangular enclosure. So we're finding the maximum possible area, so therefore we need a formula for area if we're going to maximize it. And the area of a triangle is equal to 1/2 base times height. Well, the base is right here and the height is right here. And we just found that the base is equal to square root of 90,000 minus 600x. So I'm going to say that the area is equal to 1/2, and I'm just going to go ahead and put x first, even though it's not the base, times the square root of 90,000 minus 600x. Okay, and so now I look ahead, and to find the maximum, I'm going to have to take the derivative. But this is pretty ugly. And now this isn't 1/2 times, this is 1/2 x. So if I square it, I'll get rid of the square root, and things will be a lot simpler. Okay, so I'm going to say that a squared, I'm squaring a, is equal to, and then I just have to square this. This is multiplication, so I can square each individual term. 1/2 squared is 1/4. X squared, or x squared is x squared. And the square root of anything squared is the anything. And now I have gotten rid of that nasty square root. And a product rule, and you know, we could have done it, but it would have been a little bit messy. And if I take 1/4 x squared, distribute it through, then a squared is equal to, and I simplify it, let's save some time, 22,500 x squared minus 150 x cubed. Okay. So now I'm going to take the derivative of that, because remember, if I square something, the derivative will occur, or the maximum will occur at the same x coordinate. Okay, so let's see. Let's do it this way. d dx of a squared is going to be equal to, this is much easier to take the derivative of, 45,000 x minus 450x squared. And now to find the maximum, I need to find a possible turning point. So I would set this equal to 0. And what we end up with, let's see, we could factor out a 450x, so we would have 450x times 100 minus x, and I get x equal to 0 or x equal to 100, and x equal to 100 would be where it's a maximum. To make sure, we should do a sign diagram, but you guys know what that's all about. The sign diagram will look like this, but you need to do it to make sure, which indicates that at 100 we indeed do maximize our area. Okay, so they say find the maximum possible area, so we have to finish up. So if this is 100, then that means, let's see, this is 200, but that doesn't even matter because I need the base and the height. So that is going to be an area that of the max is going to be 1/2 times the base, which we found to be square root of 90,000 minus 600 times 100, so that's going to be 90,000 minus 60,000. Can I fit it in there? Yep, I just did. Times 100, the height. And if you simplify all that, we get an area of about 8,660 square meters. All right, that is it for this this problem. Very good strategy, squaring it when squaring a function when we have a square root makes taking the derivative easier, and it's all okay because the max or min will occur at the same x coordinate. I am out, and we will see you next time.